Hello, my name is Scott Grizzard from the University of South Florida. This is Calculus 1, Lecture 5A, the basic derivative rules continued. So last time we proved the power rule. Today it's a bit of an example dump. So if you wrote on your Quiz 5A survey that Scott does not do enough examples, well this is the lecture for you, the video for you, because in this video I will do example after example after example after example. There's nothing to do here but examples. So let's get to it. So last time we did the sum, the constant multiple rule, the constant rules. We said what the power rule was, and we proved it for positive integers. These were what they were. Today we are going to do exponential notation, rules of exponents using the power rule, derivatives of some other functions, and we're going to state the power rule, the product rule, which we're going to prove next time. So let's get started here. Let's just recall these were the rules I had. Let C be constant with respect to X. Now, I need to be particular. When I say C is constant with respect to X, I mean if I nudge X a little bit, the C doesn't move. So for like Y equals 2X, when I nudge X a little bit from 3 to 3.1, Y is going to change from 6 to 6.2. But the 2 in front of X never changes, right? It's just a 2. That's a constant, okay? And there are things, so like as an example of what I'm not doing this, if I have X squared times sine of X, if I nudge X, that is going to nudge both X squared and sine of X. So I can't, neither of those are constant with respect to X. Okay, so if I have the derivative of a constant by itself, all alone, it's 0. If I have the derivative of a constant times something that's differentiable, I can pull the constant across the derivative sign, and it's C times the derivative of f of x. Likewise, if I have two things added together, I can break them apart using the sum rule. And then the power rule that we had last time is if C is a constant, the derivative of x to the C is C x to the C minus 1, as long as Cx to the C minus 1 is defined. So, for instance, at x equals 0, I can't have the derivative of the cube root of x, because then I would have an x on the bottom and the thing goes to infinity, and it's very unpleasant. But as long as the cx to the C minus 1 is defined, then I'm happy. Okay. So let's do an example of using this rule. So let's take the derivative of 6 over the square root of x. So the first thing I'm going to do here is I'm going to convert this to power notation. So the square root on the bottom is going to become a 1/2. And because it's on the bottom, it becomes a negative 1/2 when I move it to the top. So 6 over the square root of x equals 6 times x to the negative 1 over 2. Now I pull off the 6 using the constant multiple rule. And now I apply the power rule. So the negative 1/2 is going to come down. And then I'm going to have x to the negative 1/2 minus 1. And so that's going to give me an x to the negative 3/2, and I have the negative 6 over 2 when I multiply those two pieces together. Couple of things here. I reviewed this notation here in Just in Time 5, which is a lecture that should have gone live at the same time this one did or close to it. So that has all of this pre-calc that you were supposed, you were supposed to get all these forms in pre-calc, but you might have forgotten them. And it's got a couple of other exponential tricks, like things that you can use, like you can do a lot of trig using exponents, and the exponent rules about manipulating exponents. So all of that is in a optional review lecture called JIT 5, Just in Time 5. It's week 5, so that's why it's Just in Time 5. Okay. And then there's also a corresponding WebAssign that will go over those same rules again. Extra credit WebAssign. Okay, so this is my general power rule. Let's just say it one more time. Let C be constant with respect to x. If C x to the C minus 1 is defined, then the derivative of x to the C is C x to the C minus 1. We will be proving this in all its glory. This is any real constant. We already proved it. We already proved this for the we already proved this for the positive integers. We will prove it for negative integers using the reciprocal rule. That's going to be next week's problem set. Part of next week's problem set. We're going to prove it again for a rational number. We're going to use the chain rule and implicit differentiation, and this one depends on that one. And then we'll prove it for any real number, but where x is only greater than 0, and we'll do logarithmic differentiation, and we'll prove that in lecture 7a. So this one will be 6b, that one will be 7a. So we will prove all of the power rule in all its glory, but for the moment, we've only proved it for positive integers. We're just going to start using it for everything. These fractional power things, by the way. What is the number 8? A mathematician thinks of 8 as 2 times 2 times 2. So when I talk about the cube root of 8, I really mean 1/3 of the 2-ness, right? I've got the cube root of 8 is the cube root of 2 times 2 times 2. That's really 1/3 of the multiplicative 2-ness, right? I've got 2 times 2 times 2 to the 1/3, and that would be 2. So that's how a mathematician thinks about 8. Likewise, if I want the cube root of 8 squared, that's the cube root of 64. I reach for my calculator. However, I can instead think of this as 2 times 2 times 2, right, which is what 8 is, squared. I doubled the 2-ness, but then I take 1/3 of that. So really what I'm doing is I'm taking 2/3 of the 2-ness, which is 2 times 2 equals 4. Okay, so that's how a mathematician thinks about these roots. Okay, and because a mathematician is thinking about roots this way, hence the notation fractional power roots, 2/3 and things like that. Okay, so let's do some more examples. So here is the derivative with respect to x of the cube root of x. I'm going to do some algebra here. I'm going to do d over dx of x to the 1/3. Notice I've not changed there's no calculus going on here. This is just algebra. Now I'm going to apply calculus with the power rule, and I get 1/3 x to the 1/3 minus 1, which is 1/3 x to the minus 2/3. Here's a tip. So here's the tip. If you are dealing with fractional or negative exponents, actually do that step, the 1/3 minus 1. The reason why I'm saying that is that you're going to want to be careful with those. It's very easy, especially when you're dealing with negatives, to go the wrong direction. Okay? So instead of doing, you want to be careful on that. Okay? You want to be careful that you're going in the correct direction. For example, if I'm doing x squared, I'm going to wind up with an x to the first, right? I can do 2 minus 1 in my head. But if I'm dealing with x to the negative 2, it's very easy to accidentally make that x to the negative 1 instead of x to the negative 3. Okay? So anytime I'm dealing with a rational exponent or anything that's not a positive integer, anytime I've got something negative or rational, I'm going to do that step because I make that mistake all the time, and it can eat your time on tests. All right, so let's look at another example. The derivative of the cube root of x to the 5th. Well, I'm going to convert the bottom to power notation, 1 over x to the 5/3. And then I'm going to move that to the top to get x to the negative 5/3. Notice these two steps only involve algebra. Then I'm going to do the derivative using the power rule, negative 5/3 x to the negative 5/3 minus 1. And then I work out what the negative 5/3 minus 1 is. It's negative 8/3. So this is where I stop. Okay, I don't convert it back unless there's some reason to do it. Okay, unless I'm doing some kind of common denominator thing with the other side, don't mess with it. Okay, you're done. You've done the calculus. You're done. There's no need to simplify. Now, WebAssign may make you simplify it back. That's okay. That's WebAssign. When you're on a test, leave it. Just leave it. Do the minus 1. We want you to kind of subtract 1. But other than that, leave it. Just when you're done with the calculus, you're done. Okay, let's look at this one. Y equals the square root of x cubed over the 5th root of x. So what I'm going to do here is I'm going to convert everything to power form again. So this will become x to the 3 over 2 over x to the 1/5. Then I'm going to move the bottom to the top, And then with algebra, I'm going to combine the exponents. And if you don't remember how to do this, watch that JIT 5 lecture, the Just-in-Time 5 lecture, that will go over these rules with more examples again. Now I'm going to subtract. I'm going to take a common denominator of my exponents and subtract, and that is going to give me x to the 13 over 10. Now, notice this. All of this was algebra. That derivative sign is still hanging out. I'm still taking the derivative of this, which is the derivative of this, which is the derivative of this, which equals the derivative of this. And all this time, I'm doing nothing but algebra. Now I get all the way down here. Now I apply a little calculus. And I do 13 over 10 x to the 13 over 10 minus 1. And then I do a little bit more algebra to get 13 over 10 x to the 3/10. So notice how much of that problem was calculus and how much of it was algebra. And again, if you're dealing with a fraction or negative power, please write out the -1 step. It will save you a world of hurt. Here's another one. I'm going to let y equal x cubed times the square root of x plus 7 plus 5. So what I'm going to do first is I'm going to do a whole lot of algebra. So this step here is algebra. I've restated the problem. Then I've taken this and multiplied it out and did some more algebra. Here I did some more algebra with the power. Here I've done more algebra. And now I'm going to break it up with the sum. And it's okay to skip sum rule steps and constant multiple steps. Everyone knows they're there. Okay? A person who does not quite understand the problem understands the idea that the sum of the derivatives is the derivative of the sums. Okay? So you can skip the sum rule and power rule steps. Not the power rule step. The sum rule and constant multiple rule steps. But do not skip the following step. Okay, so now I'm going to do 7/2 x to the 7/2 minus 2 over 2 plus 7 times 3 x squared, right? Because I pulled down the 3 in front and I got an x squared there. And then this 0. That thing just hangs out. Do not skip that. Do not skip the idea of adding the z of this 5 becoming that 0. So what I'm going to wind up with is 7/2 x to the 5/2 plus 21x squared. Again, what's the bare minimum way to write this and still communicate sufficiently? What I'll do is dy over dx equals the derivative of this. I'll do the algebra, then I'll get here, and then I'm skipping 2 steps here to just do this. Notice I didn't write power rule, constant multiple rule, or sum rule above the equal signs, okay? For those 3, we just say, and for a constant rule, we just say, you know those, okay? Where I have to put the stuff above the equal sign is going to be product rule, quotient rule, chain rule. And chain rule's the big one you're going to want to do it for. Because if you mess up on a chain, we want to know that you meant to do a chain. I'll get to that later when we do chain rule. Okay, so now what we're going to wind up with is this, and then I drop the 0 to go to that last step when I simplify. Somewhere you have to say what happened to that 5, that it went to a 0. Okay, so again, we have some rules so far. We have a constant rule, a constant multiple rule, a sum rule, and we have the power rule. Now, notice here in the power rule, the base is moving, and the constant, the base moves, the constant, the exponent, the power is constant. That's important. Now we're going to have a new rule. This is the exponent rule. The derivative with respect to x of c to the x equals cx ln of c. Notice here, base moves, power is fixed. Base is fixed, exponent moves. Okay? So here, the c is fixed and the x is in the exponent, it moves. Here the x moves, the base moves, and the exponent or the power is fixed. Okay? Make sure you have that difference in mind because these are different things. Okay? The derivative of x squared equals 2 to the 2x to the first. This is the power rule. Okay? The derivative of 2 to the x equals the log of 2 times 2 to the x. This right here is the exponent rule. Okay, as a matter of fact, I'm going to give it a new symbol this year. We're going to call it XR. I think I called it ER and it was confusing to people. So let's try XR, the exponent rule. Okay. The derivative of e to the x by the exponent rule, by the way, is the log of e times e to the x. Well, the log of e is just 1, so the derivative of e to the x is simply e to the x. Well, that's kind of cool. Here's a function whose derivative is itself. We've got new notation for this way. We're going to call this the exponential function. And you're going to see this notation again. This idea of e to the x being written as exp of x. That's notation you'll see again, especially if you go to medical school, because you're going to have these huge things in the exponent, okay? That's going to be long, and they're going to depend on various things, various factors. This is especially true for drug loading curves, and we're going to do one of those in a problem set, okay? But these drug loading curves have nonsense in here for this x. They have huge chains, and so they have this notation exp of x. And you see this anytime you have big chains like that. So just remember that the derivative here of exp of x is simply exp of x, and that exp of x is the same thing as e to the x. That's new notation. All right, the derivative of the natural log is 1 over x. That's just a special rule, so you don't really say a rule over it. The derivative of sine is cosine, and if you had the PS3 chaser, right, some classes get it, some classes don't, depending on whether or not there's 1 or 2 classes in week 3 that we actually attend class for, because sometimes there's a holiday in week 3. But if you had the problem set 3 chaser, the proof of that is actually in there, and I'll post that in the comments too, that chaser packet. Okay, and then the derivative of cosine is negative sine. All right, so these are the rules. Just remember here that, you sometimes you see this, so 1 over x can also be written as x to the negative 1. And we'll get back into these even more later. But for the moment, they're just rules. All right, so let's mix and match them. Well, here is, if I take the derivative of sine of x plus x to the 5th plus 6, this is going to be cosine of x, which is the derivative of that piece, plus 5x to the 4th, there's a little power rule, plus 0 for the constant. If I've got 2 to the x plus x to the 5th, I'm going to have the log of 2 times 2 to the x plus 5x to the 4th. For the derivative of this thing, I'm actually going to split this up using the sum rule first. So I'm going to get the derivative of x to the 1/3, right? I converted this to a power at the same time I did the sum rule. Plus the derivative of 10 log x. Okay, and then when I do this, I'm going to wind up with 10 over x here. That's the derivative of 10 log x. And then I'm going to have 1/3. That's going to come out in front. X to the 1/3 minus 3 over 3, which will become 1/3 x to the negative 2/3 plus 10 over 3. Now, again, here, this notation here, d squared over dx squared, means take the derivative twice. So I'm going to take the derivative twice of 2 to the x. The first time I do it, I'm going to wind up with log of 2 times 2 to the x. And now I want to take the derivative once of that. Now, this log of 2 is actually a constant. Okay? It's just a number, like the square root of 3. It's just a number. There's nothing else being happening there. It's a fixed number. It's not a function. It's just the log of 2. So the natural log of 2 becomes a constant that I pull off with the constant multiple rule, which I did here. And I get the constant multiple rule. I get log of 2 times the derivative of 2 to the x, which is going to give me 2 of these. Log of 2 times log of 2 times 2 to the x. There's one more special rule over here, and this is going to be right here. This special derivative is going to be our friend in Module 4. I'm going to introduce it now. We'll see it a couple more times, but the big place we're going to see this is at the very end of the class. So let's let f be defined on some interval d and a be some base point in d. Okay, if f is continuous, then the derivative with respect to x of AUC FA of x equals just f of x. Okay, so you can think of this as a three-letter function like sine, except it's got a parameter f. And whatever f is, that's your derivative. In essence, this AUC thing is telling you what the derivative is of itself. So for example, when I come down here, I let f of x equal x cubed, and I want to take the derivative of AUC f2 of x plus the sine of x, right? So 2 is in the domain of x cubed. Okay, the interval might as well just be negative infinity to infinity, and f of x was simply x cubed. So when I take the derivative, I'm going to split it up using the sum rule, and I'm going to wind up with the derivative of AUC f2x. The derivative of this is simply x cubed. Notice I don't actually care what the 2 was. I don't care what the base point is. This thing told me what its derivative was. It was f. Well, f was x cubed. And then I'm adding the cosine, right? Because that's the derivative of sine. A quick word on this notation stuff. D over dx f of x means take the derivative of f of x. So the derivative with respect to x of f of x equals f prime of x. Now, dy over dx is the derivative of y with respect to x. That is completely different, not the same as, dy over dx is not the same as d over dx. dy over dx is a noun, d over dx is a verb. So, let's look at this as here. I've got something here. This is the x space of a function, and here's my y space. F is going to take things from x to y. This is what f does, right? It drags x values and takes them into y values. Okay. F prime takes values from x and doesn't return y values. It returns dy over dx values. And you sometimes see this as y prime space as well. But it's important to note that that's a different space. So that's what f prime is doing. F is taking things from x to y. F prime is taking things from x to dy over dx. It's a different space. It's got different things in it, right? If this is velocity, you can think of it this way. If this is miles per hour, this would be hours. This would be miles. And this would be miles per hour. Okay? So it's a different space with different units. All right, so we've gone over a bunch of basic derivative rules. We did a ton of examples. Let's go ahead and state the product rule. Okay, the product rule is as follows. Okay, let f and g be functions. If both f prime and g prime exists, then the derivative of f times g exists, and the derivative of fg of x is the derivative of f times g plus f times the derivative of g. And that's what we're going to pick up on Wednesday with proofs with the radix, and we're going to prove the product rule. Okay, so today, just to recap, we went over exponential notation, rules of exponents, briefly, but there's more of this in JIT 5, in just-in-time 5. We used the power rule to compute some derivatives. We did some derivatives of other functions, and we stated the product rule. Next time, we're going to do proofs with rabbits, improving the power rule. Okay, that's it. Thank you very much.